In the last video, we examined the method of naive inductivism, which says that good scientific reasoning involves making lots of unbiased observations and then drawing inductive generalizations from them. The main problem with this idea is that actually, when people do science, the hypotheses often have to come first. We have to use hypotheses to direct our search for observations and to understand the significance of observations. So the hypothetico-deductive method is designed to account for this. This method involves basically 5 steps. First, you decide on some question you want to answer, some problem you want to solve. Second, you invent a hypothesis by any means you like, it doesn't matter. Maybe it comes to you in a dream or whatever, but you need to have a hypothesis in mind. Third, you derive a prediction from the hypothesis. Fourth, you make observations relevant to the prediction. And finally, you determine whether those observations match or contradict the prediction. If the observations match the prediction, the hypothesis is rendered more probable. If the observations contradict the prediction, the hypothesis is disconfirmed, and you go back to step 2 and come up with a new hypothesis. Now, this probably seems quite familiar to many of you. If you've ever been taught a science, you'll probably have been presented with something like this method. If you type in scientific method on Google Images, you'll find diagrams which basically show variations of this hypothetico-deductive method. So, this is, I think, pretty plausible, and it certainly looks like an improvement on naive inductivism. It's a nice, relatively straightforward look at analysis of the method of science. So how does this apply in specific cases? Well, a nice example comes from John Earman and Wesley Salmon in their introduction to philosophy of science, and this is Boyle's law. Boyle's law says that for a gas kept at a constant temperature, pressure is inversely proportional to volume. If you decrease the volume by half, the pressure will double. If you double the volume, the pressure is halved. Let's suppose we have a cylinder containing a gas. The pressure of the gas is 1 atmosphere. It's about 15 pounds per square inch. And let's say the volume it occupies is 1 cubic foot. From Boyle's law, we derive the prediction that if we halve the volume to half a cubic foot, the pressure will double to 2 atmospheres. And so we run the test. We halve the volume by pushing down the top of the cylinder, and we see that the pressure does indeed double. This confirms Boyle's law. The hypothesis is that pressure is inversely proportional to volume. The prediction is that when we have a gas in a sealed container and halve the volume, the pressure will double. We make the observations, it confirms the law. Pretty simple, I think. Now, an important thing to notice about this is that although this is called the hypothetico-deductive method, this is actually inductive reasoning. We're assuming that a correct prediction confirms the hypothesis, and that's clearly inductive, because the observation that the observation that the pressure is doubled, well, that doesn't prove Boyle's law. It doesn't guarantee the truth of Boyle's law. So that doesn't entail the hypothesis that in all gases pressure is inversely proportional to volume. No matter how many gases you observe that display this behaviour, it's still possible for the hypothesis to be false. So the inference from the observation that when you halve the volume, the pressure doubles, to the hypothesis of Boyle's law, that's ampliative. The hypothesis goes beyond the observation. As a matter of fact, if we take Boyle's law as applying to all gases, it's false. Boyle's law is one of the laws describing the behaviours of an ideal gas, which is a theoretical abstraction. Under everyday circumstances, most gases approximate Boyle's law, but at more extreme temperatures and pressures, real gases violate the law. So, assuming that the observation supports or confirms the hypothesis, that's clearly an inductive inference. And so, in this way, the hypothetico-deductive method as I've presented it is inductive. So you might wonder, well, why is it called the hypothetico-deductive method? And the reason is that the deduction is from the hypothesis and certain specified initial conditions to the predicted observation. Right? The point is that we derive the prediction deductively. So the case of Boyle's law it looks like this. We have Boyle's law, our hypothesis that at a constant temperature pressure is inversely proportional to volume, and then we have a number of initial conditions which describe the state of the gas to begin with, and from these sort of conditions plus the hypothesis, we deductively derive the prediction that the pressure will increase to 2 atmospheres. And that's a valid deduction. The conclusion follows deductively from the premises, right? Given the truth of these premises, the truth of the conclusion is guaranteed. So we can then sort of generalize, we can say that, okay, hypotheses plus initial conditions, from these two things we can deductively derive the observational prediction. And this is sort of the opposite of naive inductivism. Naive inductivism says that you begin with observations and then inductively derive the hypothesis. Instead, on this model, you begin with the hypothesis. You specify certain initial conditions, and then you can deductively derive an observational prediction. The truth of the hypothesis, given the initial conditions, guarantees that a certain event will occur, which can then be observed. But of course, if we make the observation that was predicted by the theory, and we then take it that this confirms the theory, well, in this case, we're moving from an observation back to the theory, and that's inductive, right? So to assume that the observation confirms the theory is an inductive maneuver. I should note that this schema is, in practice, perhaps incomplete, because in practice, you can only test a prediction by assuming certain auxiliary hypotheses. Suppose we want to set up a test of Boyle's law. We're going to keep the gas at a constant temperature and then decrease the volume and see if this causes a corresponding increase in pressure to a degree predicted by the law. Well, to do this, we're going to have to use various pieces of equipment, such as a pressure gauge and a thermometer. We will need to assume that our pressure gauge accurately measures pressure, and there is a certain theory explaining how pressure gauges do this. Similarly, we must assume that our thermometer accurately measures temperature, and again, there's a theory explaining how thermometers do this. Without these auxiliary hypotheses, we could never know the volume or the pressure or the temperature or whatever, so we could never make any measurements. And this does have an important consequence. If you run an experiment and the result is not what you expect, well, maybe one of the auxiliary hypotheses is wrong. So if we test Boyle's law by decreasing the volume, but we see that the pressure doesn't increase, well, maybe we might say the pressure gauge isn't working correctly, or maybe there's some other failure in the equipment that's allowing gas to escape. So obviously, auxiliary hypotheses are used in every experimental test, and that means that in practice we have to include these auxiliary hypotheses before deriving the prediction. So we can kind of expand our schema like this. Anyway, this now allows us to define the nature of confirmation according to the Hypothetico-Deductive model. The Hypothetico-Deductive model says that an observation, O, confirms a hypothesis, H, relative to auxiliary hypotheses plus initial conditions, A, if and only if the conjunction of H and A logically implies O. So I think that's reasonably straightforward, right? The thought is, okay, an observation confirms a hypothesis just in case the conjunction of the hypothesis with the initial conditions and auxiliaries allows us to deductively derive the observation. This is known as hypothetico-deductive confirmation, or HD confirmation. So that's the basic hypothetico-deductive model. There are a number of things to note about this model. First of all, it allows that a hypothesis may be generated by any means you like. Maybe you go out and observe the world and use this to generate a hypothesis, but as I mentioned earlier, it could come to you in a dream, or it could come to you while you're out hiking, or while you're looking into a crystal ball. It really doesn't matter. So this model emphasizes the sort of creativity, the ingenuity of science. It emphasizes how science generates sort of radical new ideas. For the naive inductivist, science is algorithmic and robotic. There is a method for discovery. You make various observations and you draw inductive generalizations on the basis of those observations. This is a prescription for the generation of hypotheses. In contrast, the hypothetico-deductive model denies that there is any method of discovery. Scientists are allowed to come up with hypotheses by any means they like. And some of these hypotheses might seem completely crazy. They might not initially be supported by any evidence. There are numerous examples of this kind of thing in the history of science. So a classic example is Auguste Kekulé, who proposed that benzene molecules contain a ring of carbon atoms arranged in a hexagon. This was quite an important event in the history of chemistry. Now, Kekulé claimed that this hypothesis came to him in a dream when he had the image of a snake eating its own tail, and this made him think of a ring of atoms. So, that was just something that popped into his head as he was dreaming. Right? There's not really any rational justification for that, at least at first. So a useful distinction was proposed between the context of discovery and the context of justification. The context of discovery is how a scientist generates a hypothesis. The context of justification refers to how a hypothesis is supported or justified by testing and evidence. Now, many philosophers claim that the context of discovery is not part of the method or logic of science. Indeed, the context of discovery is often completely irrational, as in the case of Kekulé. Discovery is a question for psychologists and historians. The scientific method concerns only the context of justification. Once you have a hypothesis in mind, you can approach it scientifically, you can test it scientifically, and there is a specific method for this. But it doesn't matter how you generate the hypothesis. The second thing about this model is that it emphasises the probabilistic or tentative nature of conclusions in science. We can never be certain of a theory, because even if theory has passed thousands of tests, well, the next one might refute it. The possibility is always open that our theories will be refuted. So science is never dogmatic. On the other hand, a third thing about this is that it does allow that scientific theories can acquire increasing confirmation. As the theories pass more and more tests, they are increasingly well confirmed. So our confidence in them should grow. Observations that match the predictions of a hypothesis support that hypothesis or lend credence to that hypothesis. So although science doesn't deliver certainty, it's still legitimate to believe in those theories that have passed many tests. If a theory has passed thousands and thousands of tests, then it's legitimate to say that we can be more confident of it. We can believe it, even though perhaps we can't be certain. This all seems very plausible, but there are a number of difficulties with this model. First of all, the hypothetico-deductive method runs into trouble with statistical or probabilistic hypotheses. Consider the claim that smoking causes cancer. The obvious prediction we derive from this is that if somebody is a smoker, then they will develop cancer. But of course that's not right, because our causal claim is really probabilistic. We don't think that everybody who smokes will go on to develop cancer. Rather, smoking substantially raises the probability of cancer. So let's say we have two groups of people. One group are smokers, the other group are non-smokers. Well, even in this case, we can't logically, deductively infer that the rate of cancer will be higher among the smokers. It's very likely that the rate of cancer will be higher, but it might not actually be higher for various reasons. So, we can't logically derive that from the fact that smoking raises the probability of cancer. We can't logically derive that a group of smokers will develop cancer at a higher rate than a group of non-smokers. Maybe as a simpler example, just think about tossing a fair coin. So there's a 50% chance of landing heads. Well, logically, it's possible that this coin could land heads every single time you throw it. Logically, it's possible for a fair coin to land a run of 10 billion heads. It's extremely unlikely, but it's possible. The hypothetico-deductive model says that once we have formulated a hypothesis, we deductively derive an observational prediction from that hypothesis. But deduction is just not the appropriate kind of approach for a probabilistic claim, so it seems. If our hypothesis is probabilistic, it will never logically entail a prediction one way or another. So that might be a bit of a concern, especially given how much of science is probabilistic. A second worry is that the hypothetico-deductive method has too narrow a view of how confirmation works. We usually think that experiments and observations confirm theories as a whole, not just specific hypotheses. Einstein's theory of general relativity predicts that light passing near a large mass such as the Sun will have its path deflected due to the bending of space-time by the mass. Now, in fact, Newtonian physics also predicts light bending, but it gives a value about half that of general relativity. So one way to test general relativity is by photographing the Sun during a solar eclipse and then checking the apparent position of the stars behind it. This test was performed by Arthur Eddington, who confirmed Einstein's prediction that light bending should be about twice the Newtonian value. The point is that this was seen as a confirmation of general relativity as a whole. Right? It wasn't just a confirmation of the specific hypothesis. I don't know. The specific hypothesis might be that deflection of light by the Sun will be twice the Newtonian value. Well, it wasn't just that was confirmed. It was general relativity as a whole that was confirmed. Now, it seems that the hypothetico-deductive method views theories not as unified wholes, but as kind of aggregate collections of very specific localized hypotheses. We might worry that this isn't how scientists actually think about their theories. A third objection is the problem of irrelevant conjunctions. Let's say we have a hypothesis, H, which is confirmed by some observation, O. The hypothesis might be that plague is caused by Yersinia pestis, and the observation might be that people who have plague are found to be infected with the bacterium Yersinia pestis, whereas this bacterium isn't present in people who don't have plague. Now, the problem is that literally any hypothesis whatsoever can be confirmed by this same observation, simply by conjoining it with the hypothesis that plague is caused by Yersinia pestis. So take the hypothesis, plague is caused by Yersinia pestis and Santa Claus is real. Well, our observation confirms this, because it confirms the first part. By confirming just the first part, you also add some confirmation to the whole. If you have a conjunction of claims, if you have X and Y, and you provide evidence for X, well, that raises the probability that the whole conjunction is true. Remember the form of hypothetico-deductive confirmation, right? Hypothetico-deductive confirmation says an observation confirms a hypothesis relative to the auxiliary hypotheses if and only if the conjunction of the hypothesis and the auxiliaries logically implies the observation. Well, if the conjunction of H and A logically implies O, then the conjunction of H and H star and A will also logically imply O. So plague is caused by Yersinia pestis and Santa Claus is real implies, given relevant auxiliary hypotheses, that Yersinia pestis will be found in people who are victims of the plague. So it seems that on the hypothetico-deductive model, any observation can count as confirmation for any hypothesis whatsoever, just as long as that hypothesis is conjoined to some other hypothesis that is confirmed by the observation. Right? If O confirms H, then O confirms H and H star. So that may be perhaps a bit of a concern. A very similar problem, which is a bit more technical, so I kind of apologise for this. I hope you can follow it. This is perhaps a little bit more of a tricky problem, but it's perhaps a serious one. Let's suppose we make an observation, O. This can be anything at all. Now, for any hypothesis H, it follows that the conditional if H then O is true, right? That follows as a matter of logic, right? So this says if H then O, right? Now the reason is that logically, this is just because of how conditionals are defined logically, any conditional with a true consequent is true. So the first part of a conditional is called the antecedent, and the second part is called the consequent. And so if you have if H then O, right? H is the antecedent and O is the consequent. Now, again, logically, any conditional with a true consequent is true. And that might seem a little bit odd, but that's just how it works. In logic, at least in classical logic, conditionals count as false only when you have a true antecedent and a false consequent. It would be something of a tangent to explain why this is. So for those of you who are interested, I'll put up a link in the description. For everyone else, you'll just have to take my word for it. H then O is true if O is true. It doesn't matter what H is. Just as long as O is true, the conditional is true. So, we've made our observation O, and that means that we know the consequent is true, and that means we know the conditional as a whole is true, right? If H then O is true for any arbitrary hypothesis. And that means we can add if H then O to our background knowledge. But notice, given if H then O, given that this is part of our background knowledge, we can now logically derive O from H. So that's a simple argument, right? If Socrates is a man, then Socrates is mortal. Socrates is a man, therefore Socrates is mortal. It follows logically that Socrates is mortal from these two premises. So our hypothesis and observation have the same form. If H, then O. Okay. So if we also have the hypothesis H, we can logically derive O. So now remember what hypothetico-deductive confirmation requires. The hypothetico-deductive model says O confirms H relative to auxiliaries and initial conditions A, if and only if the conjunction of H and A logically implies O. So if we add if H then O to our background knowledge, we can treat it as an auxiliary assumption. And in that case, we can say that O inductively confirms H. Because if H then O and H, they both together logically imply O. So, so we have a hypothesis H, we have an auxiliary assumption, if H then O, and together they logically imply O. And, that means, given the way that hypothetico-deductive confirmation works, that means that O confirms H. Basically, what this objection seems to show is that the hypothetico-deductive model of confirmation entails that any arbitrary hypothesis is inductively confirmed by any true observation. I hope that is clear. As I said, it's a little bit tricky. Maybe it will help if I make it concrete. So suppose we observe that the sky is blue. Well, we now know that the conditional, if Santa Claus is real, then the sky is blue, is true. We know that conditional is true just as a matter of logic, because the consequent is true, and that means the whole conditional is true. So we can now take this conditional and treat it as an auxiliary hypothesis. And now take the hypothesis Santa Claus is real. Well, the hypothesis that Santa Claus is real, combined with our auxiliary hypothesis that if Santa Claus is real, then the sky is blue, that deductively, logically entails that the sky is blue. So, the observation that the sky is blue inductively confirms that Santa Claus is real. Again, that is, as I say, it's a bit tricky, but that's an important objection. It seems to show, if this objection is correct, it would show that the hypothetico-deductive confirmation is just trivial. Any hypothesis is confirmed by any observation. Okay, a fifth problem, rather famous problem in philosophy of science, is the Raven's paradox. Consider the simple hypothesis that all ravens are black. What sort of observations would confirm this hypothesis? Well, obviously, we would look at ravens, and if they're black, our hypothesis is confirmed. All ravens are black logically entails that if something is a raven, then it's black. So black ravens confirm the hypothesis. Pretty simple. Now the problem is that all ravens are black is logically equivalent to all non-black things are non-ravens. This is by a logical rule known as contraposition, and it's intuitively obvious. If you imagine the set of all black things, to say that all ravens are black is to say that all ravens are included in that set. So the set of all non-black things doesn't include any ravens. Or in other words, all non-black things are non-ravens. So if you say that all F's are G's, right, that's logically equivalent to saying that all non-G's are non-F's. I think that's pretty straightforward. So what this means then is that the hypothesis... So if we take the hypothesis, right, all non-black things are non-ravens, well, that's confirmed by the observation of, for example, a blue car. A blue car is a non-black thing, and it's not a raven. So, given that all ravens are black and all non-black things and non-ravens are logically equivalent, they quite literally say the same thing, it looks like the observation of a blue car confirms the hypothesis that all ravens are black. And that seems rather bizarre. We can put this in terms of our hypothetico-deductive model, right? The hypothesis is all ravens are black. Well, since that's logically equivalent to all non-black things are non-ravens, we can logically derive the prediction, this blue thing is not a raven. Or the prediction might be, if something is blue, then it's not a raven. And we check the blue thing and see it's a car, which confirms the hypothesis. So that seems kind of bizarre, because intuitively we'd probably want to say that the hypothesis that all ravens are black is confirmed by black ravens, refuted by non-black ravens, and anything that isn't a raven is irrelevant. It's rather a bizarre conclusion to say that observing cars can confirm hypotheses in ornithology. That seems rather strange. Can the hypothetico-deductivist respond? Well, Carl Hempel has some interesting comments here. Hempel actually had a somewhat different theory of the nature of scientific confirmation, but his theory also entailed the Raven's paradox. And he says that actually this isn't a paradox at all. Hempel points out that what the claim all ravens are black says is that everything is either black or is not a raven, right? So that's it, okay? That all the things in the world, they're either black or they're not ravens. Saying that all ravens are black just means that, yes, all ravens are among the black things. So we can partition the world into three classes. First, the non-black ravens. Second, the black ravens. And third, the non-ravens. So if we say everything is either black or is not a raven, well, obviously any instance of a non-black raven falsifies this claim. Also, evidently, any instance of a black raven confirms it. But it also seems quite natural to say that any instance of a non-raven also confirms it. Right? I mean, after all, right? The statement is that anything that isn't black isn't a raven, and a blue car, for example, is an instance of this. Perhaps another way to think about this, suggested in Peter Godfrey Smith's book Theory and Reality. Suppose a person comes up to you and says, I have a raven behind my back. Do you want to see what colour it is? Well, the answer is yes, because that's a test of your hypothesis. If the raven isn't black, your hypothesis is refuted. If it is black, your hypothesis is confirmed. Another person comes up to you and says, I have a blue thing behind my back. Do you want to see what it is? Well, again, you should say yes, because for all you know, that blue thing might be a raven. So checking whether or not the blue thing is a raven counts as a test of your hypothesis. If the Raven's paradox isn't really a paradox, why does it seem so paradoxical? Well, I think the reason for this is that in general, the best way to test a claim that all F's are G's is to look specifically for F's. So with ravens, there are just so many things that aren't ravens. We know from our background knowledge that most things in the world are not ravens. So checking everything that's a raven to see if it's black is a much better use of your time than checking everything that isn't black to see if it's a raven. It also might be worth noting an important logical difference. The observation of a black raven only confirms the hypothesis all ravens are black. It falsifies a hypothesis that all ravens are yellow or that all ravens are red and so on. In contrast, the observation of a blue car, it confirms all ravens are black, but it also confirms all ravens are red and all ravens are yellow and so on. Only once you've observed all the non-black things and confirmed that there are no ravens among them can you eliminate the hypothesis that all ravens are red. So anyway, those were some problems for the Hypothetico-Deductive model. There are actually a couple of other objections to this model, but I will postpone them until the next video because they are objections to any kind of ampliative inference, to any kind of use of induction, however this is explicated, whether we're naive inductivists or hypothetico-deductivists or anything else. And so that's what we'll be looking at in the next video, is general objections to any use of induction. But that's all for now. Thanks for watching.